Finally, in these talks about circuit analysis, I wanted to say something about power. Both exam questions and the quiz app will often ask you about the power dissipated or supplied by certain components in a circuit. For example, consider this circuit that we've looked at previously. Now, important formulas to know are that the power in a component is the voltage across the component times the current through the component. And if the current is going from a lower voltage to a higher voltage, then the component is inputting energy into the circuit. It's having to do work to lift that charge up to a higher potential. If, on the other hand, the current is going from a higher voltage to a lower voltage, then that component is extracting energy from the circuit. If it were a resistor, it would be getting hot. It's important to be clear about the direction the current is going in, otherwise you will end up with completely the wrong answer for the power. It's not always the case, for example, that voltage sources and current sources supply power. Sometimes they don't. It is, however, always the case that resistors dissipate power. Current always does flow from the higher voltage to the lower voltage through a resistor. Let's have a look at this circuit again and ask what power is being supplied or dissipated by each of the components in this circuit. The first thing we have to do is analyse the circuit and work out what the currents and the voltages are. We've done that before. We know that there's 4 milliamps flowing through this 3K resistor. Therefore, the voltage across the 3K resistor will be 12 volts. We know that the voltage from here to here will be 18 volts because that's what this voltage source here is enforcing. If this point here is 12 volts above ground, but this point here is 18 volts above this node here, then this node here must be at minus 6 volts. And indeed, it is. It's 6 volts below ground. We know the current going through this current source here, it's 4 milliamps. The same current will be flowing through this resistor here. I'll just move this out of the way. 4 milliamps flowing down through here. And we calculated before that the current through the 2K resistor was 9 milliamps going this way, and through the 18 volt voltage source was 13 milliamps going this way. Okay, what about the powers? Well, we'll start with this 3K resistor. We have 4 milliamps going from this node to this node through the resistor. That's from the higher voltage to the lower voltage. So this resistor is removing energy from the circuit. We could say that the power associated with the 3K resistor is 4 milliamps times 12 volts, or 48 milliwatts out of the circuit. Similarly, for the 2K resistor, the power associated with that is the current through it, 9 milliamps, times the voltage across it, 18 volts. That would be a total of 162 milliwatts. Oops, that should have been a watts. And again, that is a power leaving the circuit. Resistors always take power out of the circuit. Now, this voltage source here is 18 volts with 13 milliamps going through it. So the power of this 18 volt voltage source is 13 milliamps times 18 volts. That is, don't trust my mental arithmetic to do that one, 234 milliwatts. But this is being supplied to the circuit because the charge is being raised in potential. It's going from a lower potential to a higher potential. That's like it's being squeezed, if you think back to the hydraulic analogy. That takes energy to do. The current source, on the other hand, is taking 4 milliamps from 0 to -6 volts. That is going from a higher potential to a lower potential. That's just like a resistor. Energy is being released from the circuit when it's going from a higher potential to a lower potential. So the power associated with this 4 milliamp current source is 4 milliamps times 6 volts, or 24 milliwatts, but it's going out of the circuit. Now, energy is conserved, and the power is just the energy in 1 second, the energy per second if you like, so the power should be conserved as well. If we've got the maths right, then the total power being put into the circuit should equal the total power coming out of the circuit. And we can check that. That would predict that 234 milliwatts should be equal to 48 milliwatts plus 162 milliwatts plus 24 milliwatts. We'll just check. Yes, it is. That's good. That means that we've got our mathematics correct and energy is being conserved as we expect. The only slightly unusual thing here is just to remember that current sources and voltage sources don't always supply power to circuits. Sometimes they take power out of the circuits if their current flowing through them is going from a higher potential to a lower potential. Now, onto a useful and important result called the maximum power theorem. Here we have a circuit. The voltage source and the resistance here, you'll notice, are in Thevenin equivalent form, so you can apply this theory to just about anything which you can represent as a Thevenin equivalent network. The question is, what value of R load should you choose in order to maximize the power being dissipated in the load? And if the load wasn't just a resistor, but was, for example, a light bulb or a pump or something doing useful work, then this is a very useful result to have. You're getting the maximum amount of work out of your source here. You can analyze this in several ways. You could notice that it's a potential divider, for example, and therefore that the voltage across the load here was Vin times R load divided by R load plus R out. And then use the formula for the power in a resistor. The power is the voltage squared divided by the load, and you would get this result here. What value of R load makes this a maximum? Well, that's a maximization problem. Power equals Vin squared times R load over R load plus R out squared. We're looking for a maximum, which is a turning point, so we differentiate this with respect to the resistance of the load and set the result equal to 0 for a turning point. Differential of this is R load plus R out squared times the differential of the top, which is just Vin squared, minus what was on the top times the differential of the bottom, which is 2 times R load plus R out. I'm going to run out of paper. All over what was on the bottom squared, R load plus R out squared. That's just the formula for the differential of a quotient. If all that has to be equal to 0, then this has to be equal to this, which would give us that R load plus R out squared times Vin squared must be 2 times Vin squared times R load plus R out. that cancels with one of the square terms in here. The V-ins cancel. That gives me R load plus R out equals twice R load. Subtract R load from both sides. R out equals R load. So, if I want a maximum amount of power being dissipated in my load, the resistance of my load has to be equal to the Thevenin equivalent resistance of the source driving my load. It's known as the maximum power theorem. There are other ways to derive it as well. The important thing is to remember the very simple result. There is a bit of a trap for the unwary in the maximum power theorem, however, and I'll just warn you about it before we leave the topic. And that is, supposing you were asked this. What value of R out should you choose in order to get the maximum amount of power into the 100 ohm load? And if you don't think about it too carefully, you might remember the maximum power theorem, that R out equals R load, and answer that you should choose a value of R out of 100 ohms. And you'd be wrong, because that's not what the maximum power theorem says. The maximum power theorem says that, given a value of R out, the maximum power in the load occurs when R load is equal to R out. Remember, the power is the current times the voltage. If R load is too big, there's a very small current. If R load is too small, there's a very small voltage. However, that's not the problem here. We're not given a value of R out and asked to pick a value of R load. We're given a value of R load and asked to pick a value of R out. In this case, the optimum solution is to pick a value of R out of 0, because then all of the voltage V in appears across the 100 ohm resistor, and the power output would just be the voltage across the resistor times the current through the resistor, which would be V in over 100, or just V in squared over 100. Any value of R out that you picked that wasn't 0 would reduce the voltage across this resistor and reduce the current flowing through the resistor. So on 2 counts, it would reduce the power being dissipated by the resistor. If you know the output load and you can choose R out, always choose 0. It's a trick question that sometimes people ask. And it's the last thing I want to talk about in this series of chats about circuit analysis. We've now covered all the topics you need to attack the circuit analysis problems on the quiz app. Good luck.